Welcome to the Explainer. Today, we're going to break down a really classic coding problem, merging two sorted lists. Now, the way you'd think to do it first, it has a huge flaw, but the real solution? It's an awesome lesson in thinking backwards. Let's get right into it.
All right, so here's the puzzle. You've got two lists, both already sorted. You need to merge them. Sounds easy, right? Well, here's the twist, the big constraint. You have to do it in place. That means you can't just make a new list to put the answer in. You've got to work with the memory you're given. So how on earth do you do that without accidentally deleting the very numbers you need to sort?
Okay, let's break this down. We have two sorted arrays. Let's call them nums1 and nums2. Our job is to merge all the numbers from nums2 into nums1. And here's the key. nums1 has been set up with enough empty space at the end, you can see it as those zeros, to hold everything from nums2.
Right, so that in-place rule is everything. It's what makes this a brain teaser instead of just a simple task. I mean, if we could use extra memory, we'd just create a big new empty array and fill it up. Easy. But the whole challenge here is to be smart and efficient with the space we've already got.
So what's the first thing that pops in your head? You'd probably start at the beginning, right? Compare the smallest elements from each list and move forward. I mean, it just seems like the most logical, intuitive way to do it.
So let's play that out. We look at the first number in nums1 and the first number in nums2. We find the smaller one and we write it into the very first slot of nums1. Seems totally reasonable, but this is exactly where we run into a massive problem.
And boom, there's the trap. This is the fatal flaw. Imagine the number from nums2 is smaller. You have to write it into that first position in nums1. But wait, you just overwrote a number that was already there, a number you haven't even had a chance to compare yet. You've just destroyed your own data. This entire approach is a dead end. It just won't work.
Okay, so going left to right was a complete disaster. So what if we just flipped the entire script? What if instead of starting with the smallest numbers at the beginning, we start with the largest numbers at the end? This little change in perspective, it's the key to everything.
And this is the aha moment. You see all that empty space at the end of nums1? The zeros? That's our playground. That's our safe zone. By filling the array from right to left, we're only ever writing over those useless zeros, never over the actual important data we still need. It's so simple, but it completely sidesteps that whole data loss nightmare.
Now, to pull this off, we use 3 pointers. Just think of them as little bookmarks. We'll have P1, which points to the last real number in nums1. We'll have P2 pointing to the last number in nums2. And finally, we have P, which is our right pointer, and it starts at the very, very end of nums1. That's where our first merged number is going to go.
The algorithm is basically a super simple loop. Step 1, you look at the numbers P1 and P2 are pointing at. Step 2, you take the bigger one and stick it where P is pointing. Step 3, you move back the pointer of the number you just used, and you also move back the right pointer, P. And you just keep doing that over and over until you've used up all the numbers in one of the array. Okay, theory's one thing, but seeing it in action is where it all clicks. So let's walk through an example and trace these pointers step by step.
All right, here we go. P1 is at the 3 and P2 is at the 6. Which one's bigger? That's easy. It's the 6. So we write 6 at the very end of nums1 and we move P2 one spot to the left. See? Simple.
Next round. Now we're comparing the 3 from nums1 with the 5 from nums2. Again, 5 is the winner, so it goes into the next open slot, and we scoot P2 over again.
Okay, now it's 3 versus 2. This time, the number from nums1 is bigger, so the 3 gets placed, and this time we move P1 one step to the left. And for our last comparison, it's 2 versus 2. They're equal. In this case, our rule is just to take the 1 from nums2, so we place the 2 and we move P2. But now, P2 has gone past the beginning of its array. It's out of numbers, and that's our signal. The main comparison loop is officially done.
So that example was pretty clean. But what happens in the real world? What if one array is way longer than the other? Or what if one of them is just empty? We've got to cover those important edge cases.
Right, so our main loop stops the second one of our pointers runs out of road. But what if the other array still has a bunch of numbers left in it? We can't just ignore them. What's the plan?
And this is the last really clever piece of the puzzle. If nums1 has leftovers, we don't have to do a thing. Because we were always putting the biggest numbers at the end, any numbers still left in nums1 have to be the smallest ones. And they're already sitting right where they belong, at the beginning. But if nums2 has leftovers, We know they're smaller than anything we've placed so far, so we just need one final simple loop to copy them into the empty spots at the front.
You know, the best part about this algorithm is just how solid it is. If nums1 starts empty, it just copies nums2 over, no problem. If nums2 is empty, it does nothing, which is exactly right. And duplicates? The simple comparison logic handles them perfectly without any extra code. It just works.
So, we've got a solution that works every time and handles all the tricky bits. Now for the big question, just how good is it? Let's talk about performance.
When it comes to speed, this solution is pretty much perfect. We call the time complexity O of m plus n. Now, that's just a fancy way of saying that the time it takes to run is directly tied to the total number of items. We have to look at and move every single number exactly once. You literally can't do it any faster than that.
And what about memory? The space complexity is O of 1, or what we call constant space. This is the huge payoff for our in-place rule. We didn't create any new big arrays. We just used a few pointers, a tiny fixed amount of memory, no matter if our lists have 10 numbers or 10 million. So, at the end of the day, what's the big lesson here? It's that the most obvious path, the one you think of first, isn't always the best one. A simple change in perspective, in this case, literally deciding to work backwards, turned a messy problem into a solution that's clean, simple, and incredibly efficient. It really makes you stop and think, doesn't it? What other tough problems out there could be unlocked just by looking at them from the opposite direction?